For enhanced information extraction. I am Begüm Demir from Technical University of Berlin and Berlin Institute for the Foundations of Learning and Data. It is my great pleasure to chair this session together with Bertrand Lossau from PhilLab of European Space Agency. And he is also our first speaker, and he will be talking on diffusion models for Earth observation use cases, from cloud removal to urban change detection. Bertrand, the floor is yours.
Okay. Hi, good afternoon, everyone. So it's my pleasure to co-chair, but not only to co-chair with Begum, but also to introduce this session with this talk. So my name is Bertrand Lossau. I'm with the European Space Agency PhilLab, located in Frascati, near Rome, in Italy. The PhilLab has the mandate of scouting for new digital technologies and to leverage them for the benefit of Earth observation. And I guess this is exactly what we've done with this work. This is a joint work with the La Sapienza University in Rome. Fulvio Sanguini was an intern with us, and there was a collaboration with Horizon Papa and Professor Irene Almelini. On our side, there was myself, mostly for presenting here today, actually. But the real work was done by Mikołaj Czerkowski. So, I wanted to start this presentation with maybe a few pictures, not holiday pictures, but life at PhilLab. The thing is, when you work at the European Space Agency, you have colleagues, like everyone, in every company, in every university, that's like this. But at the European Space Agency, we have some special colleagues, because basically, and those are the people you are seeing in the picture now, those are the future astronauts. So people who will go to space, and this is a bit uncommon. Usually, you don't have such colleagues. And so they will fly in 10, 15 years from now. And for the moment, they are training, also understanding what ESA is and what we do, also in Earth observation, for instance. And we wanted to show, because we are doing a lot of artificial intelligence, to give them a glimpse of what will be the life in space, for instance, in the ISS. And indeed, just with AI, we were able to project them directly in the International Space Station. And actually, you can also go to Moon with that, because likely we are going back to Moon. But maybe it will be even further, to Mars, because yes, I mean, they are the young ones, so age 40, maybe we will be able to bring someone to Mars. So how these images are generated? Simply with generative AI. I guess you heard already about that, because, I mean, likely ChatGPT, this is a kind of generative AI, and this is something that you're using, I mean, most of you on a daily basis. This is for language and text, but the same is possible with images. So for instance, the images before was generated using Stable Diffusion, Midjourney. You have this kind of applications to make creative art and new kind of images, just generating images. And the question we had, actually it was already at the end of last year, was what can we do with this new type of AI that is coming to us? And especially because we are in the field of Earth observation. And in Earth observation, of course, this is some kind of examples of images you can do with Stable Diffusion, with Midjourney. You can do beautiful artwork, you can do comics, maybe. You can even generate very realistic images, so to illustrate things, maybe for VFX, for movies. Okay, great, but in Earth observation, how can we use that? So maybe, and I hope actually that some people in the room have ideas. We had a few also on hand, and we wanted to test it. And this is exactly what I will present today. So basically explaining for those who are not familiar with this topic, what are the denoising diffusion models, so the kind of generative AI models that we've used here. And we'll try to show and assess how it can be used for various Earth observation use cases. So, basics of diffusion. Usually everyone is, well, especially in this kind of conference, is familiar with I don't know, a UNet for classification, segmentation of Earth observation data. You have your data, your UNet model, and you're able to predict a land cover map, for instance. You have half the poster with, I mean, not half the poster, but you have plenty of posters so to explain you how to do that. Here, this is a quite different thing. Basically, the idea is to learn to go from noise to a real image. And you do this step by step. So basically, this thing will work. Oh. No, not what I expected. Okay. So you still hear me? So basically, starting from noise, the idea would be to be able to produce a real image. Okay? This means that you need a kind of network that is able to do all these little steps, step by step, to go from noise to something that is less noisy, that is, oh, you start to recognize something, and at some point to a real image. This is exactly how the model is working. Of course, this network has captured a lot of information to be able to do that, and this is also why it is called a generative model. That is, it is not only capturing the information on how to have the posterior probability of something, like when you have some data and you get a classification map, a land cover map. No, here it really learns how the data, what are the statistics of the data. And from that, indeed, you are able to reconstruct and even to invent images, in that case, by applying this process. How is it trained? Actually, by doing exactly the reverse thing, because going from noise to real images, this is difficult, of course. But adding small steps of noise to an image, like here, starting from here, and then adding more and more noise, this is something that anyone can do. And if you have this, you have also the ground truth to learn the reverse step by step. Okay? I hope, this will be the only summary I will give, so I hope it was clear enough. We can also discuss at coffee if you want more explanation. One example, so diffusion models, you can generate just like this some images. What is very interesting is that you can also mix with other information. You can constrain that by text. So, for instance, you start from noise, but you constrain with text like I want, I don't know, a city picture seen from above with a swimming pool, with a road, a forest nearby. And the diffusion model should be able, when correctly constrained, to do that. We can also do in painting. We have several variants. I won't enter here in the detail because I want to move to this part. So the first use case we used was cloud removal. So after cloud detection, replacing what was hidden by the cloud by something. And this is the easy part actually of in painting. It worked pretty well. For this, of course, we retrained generic stable diffusion on EO images. And as you can see here on the images, this is input, the cloud detection mask, and the corrected version. So, what is the good thing here? Actually, it works. And there are benchmarks of cloud removal, so very, very nice. Personally, I'm not very happy and very, I always have doubts about the real utility of such an application because who needs invented EO image? Earth observation, remote sensing, this is about measurement, so you don't want to invent stuff. But for instance, one perspective of this is when you can have for instance, cloud diagnostic sensor data like SAR, Sentinel-1, for instance, more or less at the same time, and be able to translate the SAR data in something that is understandable by everyone, like in kind of Sentinel-2 style. This, for instance, would be a real application, so a perspective for pursuing this use case. Another use case we try to assess is actually for dataset generation. If you have done a bit of change detection in your life, you know that it's very tricky just to annotate the image, because first you need to have the same location at both dates, and then just to have the ground truth to learn exactly what was the change map. This is, I mean, for human interpret, this is quite tricky. So actually, we did it a bit differently. We started from images. We had some masks, just random, connected components into the region. And we generated some invented images at the same place. With that, actually, you have exactly what is needed to train another AI for doing change detection, because you have the before image, the after image, and you have the mask of change. Perfect. Okay? And this, actually, this is a data set that we've put open for public, so if you want to test it, please do. Especially because now the real task is to assess that on a downstream task, to be able to test if you can train a change detection network on a big data set created this way and apply that on a real use case. So if someone is doing change detection in the room, please try it and give me feedback. I would be very happy to discuss that with you. The third use case is maybe a bit more exploratory. It's also about inventing new applications. Because the previous one, those are real use cases that we are already using in Earth observation. But we can also invent maybe what could be the future. And for instance, urban replanning. That is, you have a city, you could imagine how it would look like if you made this kind of change. Because maybe we don't need all these urban motorways, we can replace that by green areas. I would prefer that, but you can have also lots of change. What is the impact of installing an industrial district with respect to other things? And this, for instance, is kind of smart visualization of testing of possibilities could be very useful, for instance, in digital twinners, if you want to play simulation scenarios and what-if scenarios. So we have a nice visualization tool. For the moment, lack of interactivity and control. I don't think that urban planners would use that like this. But perspective here are to add text-to-image, also some kind of control interface so you can change what is happening. And of course, it could be done also with street view images in the meantime. So, to conclude, a bit of, I hope I won't be too much polemical, but remote sensing is largely about measurement, sensing, observation, so something that's really factual. So it's a bit difficult to find use cases for generative models, but I think here we have set a few possibilities, and I think that actually there is a great potential for many new applications in the next years. Maybe applications we don't think about right now, we not even know they could exist. One issue maybe in doing that will be to also incorporate responsible AI and ethics in that, because like with text, you can generate fake news also, you can generate fake images, and we know that wars have been started just because of satellite or aerial imagery, which was a bit corrupted. This is also a tool to do that. So indeed, it has to be done with ethics and responsibility. I wanted also to discuss, actually, so a project of AI for good, which is a new project we started at the PhilLab actually last week. We had the kickoff meeting. This is done by Nonsense Center in Norway. And they will use this kind of models, diffusion models, for doing downscaling, super resolution of CIs. And starting going from the model, incorporating some observation, and generating at a final resolution some sea ice. So this to study how the sea ice is evolving, also to find routes for boats and so on. And to conclude, I mean, you can see the various use cases. Yeah, basically this was also to show the way we work. We have small ideas at PhilLabs, then they are done in ITTs, in other contracts that we are contracting with you, with the community. And hopefully this will go to business development, and you will have in a few years business application developed by you for also scientific applications for the benefit of Earth observation. That's all for me. If you're interested in the topic, so first, thank you for your attention. If you have a question, I will answer it briefly. And there is also a spotlight talk at 4, I guess, by Aurélien Lac, who is just there. So on this topic, so please listen also to what he has to say. Thank you.
So we have time for a very quick question. Yes, please.
Maybe Piotr, we can let the people in the because
of course. Thank you. Thanks. So Francesco Pignatale, Telespazio Germany. Just one question: is also thinking about the safety of this in painting and diffusing these images that are, as you said, not really real and might be dangerous for the people that want to use it. Are you thinking about some metadata, some hidden mark that can tell to the user that actually this data set is created by AI? I mean, is there a method that you're already thinking to avoid the diffusion of these fake images?
This is a very good question. So, I mean, like for Midjourney images, I mean, for artwork, there is no such thing yet. So indeed, that's a crucial issue that we have to think about that right now. Of course, there are ways of doing that in the metadata, but the metadata are so easy to cancel, so that it's also about, I mean, so we can imagine mechanisms with blockchain, for instance, and this kind of things, and we are investing also blockchains, not exactly in that domain, but this could be a solution. But also what you say, and what I try to convey as a message is that the world of Earth observation will change also with that, and we have to be ready, because indeed we have lots of images and we cannot trust them anymore. So indeed, this is a big work that we have to do in the next decade.
Okay, maybe we can have the second question also.
Yes, I have the technical question about the stable diffusion. I mean, diffusion is the function from point T to point T+1. Is it for the same? I mean, for different time steps, is it the same network or different networks?
Yeah, very good questions. It is the same network, but when you train it, you also incorporate the timestamp. Sorry. So indeed, you know that at this timestamp, you should have this kind of transformation, and there are enough parameters in such a network to be able to adapt. Yeah.
Thank you.
Okay, thank you very much, Bertrand, again.
Thank you again. Just to introduce briefly the next speaker, Aurélien Lac is a former basketball player, but today it's not to talk about that, but about super resolution of Sentinel-2. He is with Thales, but it's a joint work, as you see, with many partners.
Thank you very much. And thank you for the presentation of this diffusion model. So hello everyone, I'm Aurélien Lac, and I'm here to present to you our project about super resolution applied to Sentinel-2 for Earth observation applications. For this project, the aim was to design a model, a deep learning model, that was able to do super resolution on all Sentinel-2 bands to go from 20 and 10 meters up to 5 meters. So as you can see here, we have 2 methods and also 2 models for 2 types of bands. The first one used Venus as a high resolution reference. So we train this model in a supervised way. And the other model for B11, B12, we did not have a high resolution reference. So we trained it in a different way. I will talk about that later. But the real focus of this project was actually the validation that we did on actual Earth observation applications to really validate the potential use of those kind of techniques for real-life applications. So just to be sure that we're all on the same page about resolution and super resolution. Resolution in an image can refer to different things, like pixel count, spectral resolution, temporal resolution. Here we are talking about spatial resolution, and super resolution will aim at augment that resolution. For the example, those 2 images are the same number of pixels, but the spatial resolution is not the same. So the basic idea is to go from this kind of image to this kind of image. And for training our model, our first model for the band B2 to B8A, we used open data set called Send to Venus. It's an open data set on more than 100,000 patches. It's a data set that is made for super resolution, so the focus was really on the conservation of so that the Sentinel-2 and Venus had the same geometry and radiometry. But of course it's 2 different satellites, so it's not perfect, as we will see. And the architecture we use, or the generator for super resolution we used, for those who know, is ESR-GAN. It's a really famous architecture for super resolution, and we trained it with the GAN loss, with the real ESR-GAN architecture, which is a unit discriminator with a which is a unit discriminator. Sorry. For the B11 and B12, as I said, we did not have a high-resolution reference. So we used the WALD protocol. So the basic idea is to train our network with the same architecture, by the way, in lower resolution. So to go from 80 meters to 20 meters. And at inference, we are using the same model, but on real resolution. So as I said, the dataset is made for super resolution, but it's not perfect. If we compare the two images from Sentinel-2 and Venus, you can see really small changes. So I took like worst examples from the dataset, but you can see geometric deformation and radiometric deformation. And so if you train the model with a naive method, like just using the paper of ESR-GAN, for example, the network can learn those geometric and radiometric deformation. As you can see, the input of the model and the output of the model, this is really not what we want, of course. And as you can see, for example, the Venus reference image, you can see that the model kind of does an interpolation of both images. So it kind of learns the transition between the 2 satellites. So basically the solutions we find we found 2 main solutions to that. The first, for radiometric deformation, we used a separation of losses between high and low frequencies, so that we make sure that the network really keeps the low frequencies from Sentinel-2 and just learn to adapt the high frequencies to actually do super resolution. And for the geometric deformation, we carefully choose the depth of the network, so that is powerful enough to do super resolution, but not powerful enough to learn those slight geometric deformation. Those solutions actually worked pretty well. we add visually, at least the results are convincing on the 20 meters bands especially. This is visually pretty striking. We can really see the gain in resolution. Also for the B11 and B12, even if it's another network trained in a lower resolution, the gain of resolution is really important. As you can see here, we can see lines that we couldn't see before. As for the real validation, independent of Earth observation application, we used we analyzed all the bands with classical metrics. We also analyzed the biophysical indices, and we made sure that the data from Sentinel-2 was really the same at the end, at least for the low frequencies. We also checked the geometric distortion. As for the Earth observation dependent applications, I will present here two applications we use for validation. The first one was done during the project and done by MEOS on water resources estimation. And the second one is an additional use case we've done recently with our intern on the land cover maps. For the first one, MEOS used their algorithms that they use usually on Sentinel-2 for real application, here water resources, and they try to compare what are the results if they train the algorithm on super resolved data. And the results were very good, especially on small objects, on small areas of water. Here you can see we had more than 3 times more small object detected with super resolution, and up to 16 times more surface areas for the super resolution. And with our algorithm, we did not have an augmentation of false positive. So this was a really great news. Visually speaking, we can see here, I hope, that in dark blue you can see all the new water bodies that we can detect with super resolution, and in the light blue, the one that were already detected with Sentinel-2. You can see a substantial improvement. If we zoom in, you can also see that even if the water body was detected before, it's way more precise, and it's way more accurate, at least with the ground truth we can have here. As for the land cover maps use case, we use IOTA2 tools that are already used on Sentinel-2 for land cover map generation, and we compared the output of the algorithm if it's trained again on Sentinel-2 or super resolution of Sentinel-2. And again, you can see substantial improvements, especially on small objects, like for example here for a bridge that is not detected with an algorithm for Sentinel-2 or for Sentinel-2 with a big sampling, but is detected with our super resolution algorithm. Another example here for a small path in fields, where you can see a way more precise detection. It's again an example of a bridge that is detected here in the middle for super resolution. And the last example on the roads that are almost completely all detected with when using super resolution before the training. So our results were really satisfactory to us. We really hope that we show that super resolution can be a very useful procedure to use in a wide range of application. Actually, we will soon there will be an on-demand processing available on Thales services platform. of course, if you have any question on how it works in more details or how you can use it, do not hesitate to contact me. And thank you for listening. That's it.
Thank you, Aurélien, for this talk. Maybe we have questions in the room. Yes. If you can please.
Hi, thank you for the presentation. My question is, so how did you compare what algorithm did you use to detect the water segmented before applying the super resolution and after applying it?
How do we compare it?
Yeah. So what network was used, or what was the procedure to use to actually detect the water?
So for the first use case?
Yeah, for the first one, the water detection one.
Okay.
Yeah. So.
We used the same algorithm, but trained on Sentinel-2 classical data. We use the algorithm, we see what water is detected, and then we do the same thing, but for super resolved data. So we generate the Sentinel-2 data. We train the algorithm for detecting the water with the same reference, and we compare the results as we can see here. But we do 2 trainings.
So it
was
was
that the question?
Okay, yeah, I get it. Okay. Thank you.
Okay.
Hi, thank you very much for the presentation. I have a question. I'm wondering, what is your intuition on that? If you're doing super resolution, then you're hallucinating structures into the images that you see based on common sense that you have trained into your model. Now, what is your intuition? So this is in itself, I see it a bit skeptical. So, and I was wondering, what is your intuition? Where are the limits? There are certainly cases where you're not able to get more information out there. Here you're helping segmentation networks to have better segmentation, which is fine. But do you see limitations with respect to the resolution, how far you can improve the resolution?
No.
Have you noticed difficulties because what the network is seeing there is not necessarily there? So I'm just wondering in that direction, what are your insights?
That's a really good question. And actually, there is limits. That's why in this work we stopped at 5 meters, so that the 10 meters band we do 2x super resolution. So in this case, as you can see in the top row, this is more of a sharpening that's happening here. Of course, if there is an object like a small tree that is, I don't know, 2 meters or 3 meters, with Sentinel data, you will not be able to do more with that. But for example, for objects that are thin, that are long, for example, the intuition is that statistically you can, the network learn to know that you can sharpen the image in a way that statistically is closer to reality as 5 meters. But if you want to go further, to do times 4, times 8 for super resolution, of course, it depends on the application, but for a lot of applications, it's not a good idea because you will hallucinate a lot of things. As for here, indeed, we do a times 4 super resolution for the 20 meters band, but the thing is, we proceed with our architecture. We proceed all the bands at once, and so the 20 meters band are helped by the 10 meters band, so there is a kind of a punch happening. So, but we wouldn't have those kind of results if there weren't 10 meters band to help. That's why. And also for the punch happening here, in the inputs of the network, there is not only B11 and B12, there is all the bands from Sentinel-2. So the 10 meters band also, this is not the case here, but sometimes you can have between bands some shift, like a little shift, so you can have more information that the network can use to do super resolution. I hope I...
That's good. Thanks.
Okay.
Okay, thank you very much. Now let's move to the next speaker. He is Luca De Felice from Joint Research Center of European Commission, and he will be giving a talk on surface water detection framework using Sentinel-2 and hierarchical random forest models.
Thank you. Okay, it's going. Thank you for joining me. I'm Luca De Felice from the Joint Research Center. I'm quite excited today to present our work on about water classification using Sentinel-2 imagery. In this presentation, we will discuss about the methodology that we followed, that we developed with my colleagues, and the data set that we used for train our models, and of course the results that we obtained. I'm not gonna to spend too much time on the importance of surface water monitoring. For sure, it's important, especially after in the context of the European Union Water Framework Directive, to have tools and the Earth data, Earth observation data are instrumental to align with the EU water policy and related activities like common agricultural policy. And our methodology will be able to support EU water framework directive. But before to delve into the descriptions of our methodology, let's start from the beginning where we got inspiration. Many of you probably may be familiar with the Global Surface Water Explorer, which is always a GRC project, which maps at global scale 38 years of water bodies using Landsat data at 30 meters resolution. And it classifies water at monthly level. So we have 454 monthly water maps using multiple images within that specific month. Building upon the knowledge and experience that we gained with the development of Global Surface Water Explorer, we have embarked in a new project using the Sentinel-2. We want to improve the spatial resolution because we are using 10 meters resolution. The output is 10 meters resolution, but also the temporal resolution. But differently from the Global Surface Water Explorer, we want to have a system, a methodology that is able to classify the single sheen. So the objective is quite clear, the task. We want to detect open surface water pixels from Sentinel-2 imagery. We fixed some requirements. First, I already mentioned the single sheen detection capability. We want to base our classification only on spectral info, and we would like to have as outcome also the pixel uncertainty, or at least a proxy of the pixel uncertainty. In order to train our models and let's say validate also the performance, we created a manually annotated dataset, which is called Sentinel-2 Gold, which stands for Global Open Label Dataset. It's now publicly available. There is the DOI, the link at the bottom. It consists of more than 50 million points. It spans from March 2016 to August 2021. It's based on manually visual inspection, manually drawing polygons. It consists of 15 classes, and it was designed in order to be versatile, not in order to go beyond the water detection. By the way, for our specific task, we considered 3 classes. Water, land, of course, but also those invalid classes, like those pixels covered by clouds, cirrus, and shadow, topographical shadow, or cloud shadow. To achieve our goal, we had decided to employ the supervised classifier, random forest models, which It's widely used in enhanced classification algorithm and has shown great success in other various tasks like land cover studies. In terms of feature generation, we started with the original Sentinel-2 bands at 10 meters and 20 meters. We discarded those ones at 60 meters. We downsampled the 20 meters to 10 meters. We created additional features by the combination of those bands. We used the most used in the literature water indexes like NDWI and DVI. We created additional features by combination of bands using the U saturation value color space transformation. And finally, we also used the 3 by 3 pixel average for all those features for a total of 50 features. As regards the training strategy, we implement different training strategies in order to optimize our models. The first training strategy was to use one single classifier, random forest classifier, with 3 classes. A second type of strategy was to use a sequential set of random forests in order to to classify firstly the invalid pixels and then the land water last final classification model, let's say. The best results were obtained by specifically by 4 random forest models. The first 3 ones are those which classify invalid pixels. The first is one about clouds, then cirrus and shadow. And the last one, we call the first classifier pre-classification models. The last one is that one that actually classified the rest of the pixels in land and water. Everything, all the methodology and the system was developed, trained, and tested and also visualized on the big data analytics platform of the European Commission. In order to ensure the reliability of our model, we of course validated. We set aside the 30% of the points, and here you can see the results, and you can see also an example. On the left side, you can see the Sentinel-2 image in RGB, and on the right side, our detection, water detection in action, with the water highlighted in yellow. So the results appear to be very promising. Here is another example in the Amazon forest about a river. But we were not happy to validate only against our dataset. We want to validate also against an external dataset. We chose to use the dynamic world training dataset. You may be familiar with dynamic world. Probably it's a 10 meters land cover classification by Google World Water Resource Institute. And they released publicly their training dataset, which was provided with 3 different experts that labeled the patches. Here there is an example, and there is, of course, the results are still very good, very promising. And on the left side, you can see the original Sentinel-2 image. In the middle, our water detection with the water in yellow, and on the right side, the patch, annotated patch by dynamic world. While our water classification methodology has shown promising results, we have to acknowledge that we encountered issues. Sometimes in certain areas we got some issues with cirrus and haze. At the top of the picture, there is the Sentinel-2 and our water detection, and with some problem with the haze. At the bottom there is some example about the ice and snow. However, it's worth noting that our methodology has demonstrated very good performance, for example, in detecting shadows. Here you can see an example in the mountain zone. Here I'm showing you a comparison. We started from the Global Surface Water Explorer. Now there is a comparison between the monthly layer of Global Surface Water Explorer and which is, we need to take into account that it's a monthly aggregation, and the Sentinel-2 detector in action. You can see in red the water detected by Sentinel-2 the classification algorithm. You can appreciate the final resolution. Here is another example. We were able to catch, to map the flooded event in the Demidov village in Ukraine in April 2022. On the right side, you can see the flooded event, and on the left side, the 1 year ago, how it was the status. This one is our Sentinel-2 detector in action, let's say. So I'm coming at the last slide. We have two main outcomes. The first one is this Sentinel-2 water classification, surface water detections, which will support the EU policy, water policy objectives, and specifically for the European Union Water Framework Directive. But we released also a valuable reference dataset that could be used for other classification purposes and for other machine learning tasks. It's fine with me. I'm available for any questions.
Yeah, we have time for a quick question.
Actually, I have...
I have maybe a silly question, but when you are detecting shadows, basically the shadows could be detected through geometry of the landscape and, of course, position of the sun. So do you use this information about the structure of the, about height of the Earth and, of course, the position of the sun and satellite, and how the image was acquired during the acquisition process?
No, we are not using at this stage this level of information. We tried, honestly, to develop something similar, but then, if you remember, there is a slide that we want to fix some requirements. We want to base everything on the spectral info at this stage. It's something that we want to develop maybe at a second step.
Okay, thank you.
Thanks.
So I will have one question also. I was a bit curious about the previous slide on this one. I wanted to know, with this kind of techniques, what is the gain you expect when you will put that maybe at some point in operations? Because you see, especially at GRC, you are doing lots of disaster mapping, disaster response. So on which kind of dimension of the problem do you expect some gain with AI feature extraction?
We have some plans, of course. We didn't discuss, not yet very deeply with this, but for sure the possible applications are different, and not only crisis management. As you can see here, there is a flood event, so one of the requirements was exactly to have a Pershing classification, which means that in theory we could use that as also in near real time. So it could be definitely usable by crisis management offices, institutions, but also for water resource management, I would say.
Thank you very much.
Thanks.
Is there any other question from the audience? Okay, thank you very much again.
Thank you.
So our next speaker is Clément Dechaine, from the Magellan company, located in Toulouse, France. And he will... yes,
I'm not Clément Dechaine.
You're Jean, actually.
Yes,
this was, sorry for not what was planned on the schedule. So Jean Bojo from the CNES, because anyway, there is Magellan, CNES, but also lots of companies and research institute from France in this beautiful project that is now ended, I guess, but that started 4 or 5 years ago, AI for Geo, and Jean-Eudes will give us a glimpse of what happened in that project. The floor is yours.
Thank you. So I'm Jean-Eudes Bojo, and I'm postdoctoral researcher at the French Space Agency. So Clément cannot be here because he cannot attend the conference. So I have the pleasure to give you an overview of our work on semantic 3D reconstruction using satellite imagery. So let's start with a bit of context. Maybe you are already familiar with the AI4Geo project, but let me introduce again the project. So the AI4Geo was initially set up given the increasing demand of 2D and 3D information, geospatial information, observed in the wide range of sectors like smart cities, environment, autonomous vehicle, and also today we are talking more and more about digital twins. But producing this information requires costly manual operation that inhibits scaling up. Therefore, AI4Geo aims to automatically produce semantic and geometric geospatial information at a global scale, making use of very high spatial resolution satellite images. Of course, we want to leverage innovative AI methods and big data technology. And the project is funded by the French Public Investment Bank. Our 3D modeling objective is centered around the level of detail concept in the CTGML initiative of the OSGeo. And we have targeted reconstruction from the load 0, which represents ground footprint, to load 2, with height and roof represented. We also want to extend the general focus on building by incorporating a broader representation of urban area with classes like vegetation, roads, railways, and so on. Well, I'm going now to explain in detail the AI4Geo 3D pipeline, starting with the input data, which are played images, basically 3 stereo acquisition, which are pan-sharpened at the 50 centimeter spatial resolution and orthorectified and calibrated in top atmosphere reflectance. So from the multi-view images, we use open source software to produce also digital surface model and also digital terrain model. So the digital surface model is produced by Stereo Machine using the car software developed at the CNES or the MIC software developed by the French Mapping Institute, IGN. And the DTM is extracted based on the DSM using a recent pipeline we developed at the CNES called Bulldozer, which is also open source. Then we conducted the deep semantic segmentation using the image closest to nadir, and we are interested at least in 6 classes: building, vegetation, low or high, road, railways, water, and water classes. So we have annotation coming from OpenStreetMap and also private annotation, which amount are smaller than the OpenStreetMap. For the model part, we have encoder-decoder architecture, typically in the UNet style. For example, using an efficient net encoder and a refined net decoder. And we have 2 settings, so a multi-class scenario where we train one model to recover all the classes, and a monoclass scenario when we have specialized model per classes. For the 3D modeling, we need a vector representation of our land cover category. But as we know, one limitation of deep semantic segmentation model are difficulties to produce sharp segmentation, which is, for example, needed for building. And of course, end-to-end polygonal method like the frame field learning or polyworld can solve this issue, but mainly due to the spatial resolution of the played images and also noise in the ground truth. We got poor results with this model in the project. So our solution is to apply a regularization, so to generate the load zero with refined footprint for the land cover category. So thanks to a benchmark we conducted in the project, we adopted the Jordan algorithm to regularize the building object, which you can see which can make a sharp edge with regularized footprints. And for the other classes like vegetation, road, railways, or water, we use the Ramer-Douglas-Pucker algorithm, which is a SIM simplification, polyline simplification algorithm. Well, when we generate the load zero, the next step is to produce 3D information, so the load one. And in the project, we have developed two methods to produce the load one. The first is called mesh cooker, which is an object-based semantic mesh method. So it aims to produce meshes object per object. And basically, we extrude the object of interest using to reconstruct border or wall using the height information thanks to the difference between the DSM and DTM. And we triangulate all the object of interest points to build the surface or ground and roof. The second method is called unique semantic mesh, which, as its name suggests, aims to produce a closed and unique mesh for the entire scene. So in this case, we triangulate only the DSM and label each vertex according to the semantic map. So it can result on a very large semantic mesh. So we need a simplification, and this is achieved in the project by minimizing a geometric and semantic cost. It's all for the current state of development of the AI4DO 3D pipeline. Let's now have some visualization. So we use the mesh cooker to reconstruct 3D information on a 4 kilometer square area of the Montpellier city center, which take about 30 minutes of processing to obtain the object-based semantic mesh. And we have about 5 million of faces for the building class and 2.5 million of faces for high vegetation. The unique semantic mesh is used to process the smallest area of 0.3 kilometers square of the Montpellier city center too. And it takes about 4 hours of processing on a single CPU, simplifying 2.75 million of faces into 22K faces. But overall, we can see that our results with the mesh cooker are quite better than those with the unique semantic mesh. But overall, our results are tightly linked to the quality of the input DSM, DTM, but also the semantic map. To sum up on the AI4DO 3D pipeline, so we are able now today to produce 2D and 3D geospatial information, load 0 and load 1. We focus not only on building, but also on vegetation, road, railways. And this 3D geospatial information can be used for various downstream tasks or simulation in urban planning, but also disaster management. But as we saw in the visualization, so the quality of the result are linked to the DSM and the segmentation step. So enhancing this step is key for improvement. But good news, we are working now with played Neo data, and we're already observing some improvement in our segmentation, but also in the 3D information we are producing. So yeah, is all for my presentation. Thank you for your attention and any question you may have.
Thank you, Jean-Eudes, and also especially perfectly on time. Congratulations. You have the award of that for today, I guess. If you have questions in the room, please raise your hand so we can bring you a microphone. Okay, we have a shy audience today, so okay, I will start. Maybe with one of mine, but I expect that there will be another one after. So, okay, no, please do.
Sure.
Yeah.
Just to, can you hear me? Yes. Thank you for the presentation. If I go back to the presentation we have about the forest yesterday morning, yes. Is it a way to use the same method for trees or to count trees and to see different A's on the forest, for example?
You mean the presentation, the same presentation on the AI4Geo project, yes?
Yesterday.
Okay. But in the project, currently in the project, we are not really working on forests theme, but I think so we can. We have in the project some pipeline for change detection, which can be also conducted in 3D. Basically, we have DSM for a time step 1 and a time step 2, and we try to detect the change between the two time steps. So I think this kind of approach may be used to detect the height of forests. So yeah. But actually, currently we are not working in this direction, that direction.
Okay, thank you.
Yeah.
Okay, maybe another question. So, okay, I will ask mine in that case. If I remember correctly, one of the use cases which were targeted by AI4Geo was smart cities. And could you explain to us how you go from what you just presented to maybe what can be useful for smart cities?
Okay. So what I can say before is in the AI4Geo project is industrial partner have his own case application. So basically, in the Airbus is already using. So they treat the information we produce to have some kind of simulation. So basically, we have pollution. So given the direction of the wind, what will be, we simulate what will be the propagation of the pollution. So this kind of application. And also in the project we have the Toulouse Metropole, which is an early adopter. So basically its use case is to know what is the new building, what is the new building. So they are interested in counting the number of buildings. And also we have the QuantCube startup, which is interested in knowing what is the new floor which are added in the building. So we have this kind of application in the project. Yeah.
Okay, thank you very much.
Thank you.
A round of applause.
Okay, now I would like to invite our next speaker, Chiara Leuzzi from Altec Space, and she will be giving a talk on a tool to investigate and demonstrate the use of machine learning in various areas of GNSS domain. The stage is yours.
Thank you. Hi everyone, I'm Chiara Leuzzi. For those of you who were not here this morning, I'm from Altec. I work in the... Oh, sorry. Okay. I'm from Altec. I work for the Data Processing System and Scientific and Technological Application group. And today I will talk to you about the GMLD, that is a tool we developed during a project in order to investigate and demonstrate the use of machine learning in different areas of the GNSS domain. A brief introduction about the agenda. I will talk to you about the objectives of the project, an overview about the GMLD, that is the platform we developed, the list of applications that we selected and implemented and integrated into the system, then a focus on the prediction of daily maps of the ionosphere, and finally some conclusion and follow-on activities. So the main objective of the activity was to assess the usability of machine learning in the techniques in order to improve data availability or quality of the GNSS data. In particular, the project was performed during a NAVIS Element 1 project, and so it was funded by the European Space Agency. The project was conducted in collaboration with some GNSS domain experts from Politecnico di Torino, also some machine learning experts from the same Politecnico, in particular belonging to the Department of Electronics and Telecommunications. The results of the activity provided a demonstration of the usability of machine learning, at least in some areas of the GNSS domain, the implementation of those machine learning techniques that we selected for each applications in order to build some tools that simulate some segments of the GNSS domain. And finally, the implementation of a framework that enabled scientists to, or the GNSS domain experts to extend the models to other use cases in the same domain. The GNSS machine learning demonstrator, that is our GMLD, is mainly composed by 4 applications that implement the machine learning models that we selected. The models have the scope to predict some missing information or to search for possible error sources. We selected the application in order to cover different kind of GNSS domain data. Apart these 4 applications, we have some shared modules that are used across the different applications, and these modules have the capabilities to read and write GNSS data, and in particular to manage the machine learning life cycle, machine learning model life cycle, so enable to define, train, validate, and run the models. We can see an high-level schema of the demonstrator. In general, we can say that the demonstrator provides capabilities to implement the applications as a composition of 3 main modules that are the data indexing and transformation, the module related to the building of the machine learning models, and finally the data output transformations. The input are a file of GNSS data products. They are stored in several repositories and then accessed by the applications. In particular, we used MinIO as object storage and InfluxDB time series database. We have a flow engine that has the objective to manage the pipeline. In particular, it allows to define, coordinating, and monitoring the pipeline related to the application, but also other data management flows. It is based on the Aperture flow. So each pipeline is represented by a direct cyclic graph. We have, for each application, mainly 2 kinds of application. The first one is the development application. The second one is the production application. They enable the data scientists and the domain experts to build the models and then to run them into the application. In particular, we have the feature extraction that, of course, is dedicated to extraction of those information that are then provided as input to the machine learning models. Then we have the module related to the machine learning activities. Of course, it is different among two pipelines because in the first case, it enables to build and train and validate the model, while in the second case, it enables to serve, to deploy, serve, and run the model. We integrated a machine learning registry. In particular, it is based on an instance of MLflow in order to record all the experiments, to compare them, and to catalog the trained models. Finally, we have a post-processing module that consists of a data product generator. We build the product in classical standard of GNSS products in order to make them ready to perform additional analysis or the subsequent phase of the GNSS performance assessment. GMLD is not only a standalone software, it was also deployed into the GSSC Now platform, that is the GNSS Support Science Center realized by ESA. In this case, each GMLD corresponds to a data lab, which is a container that encapsulates different tools. In our case, Jupyter Hub exposes the applications in the form of notebooks. So each container provides a set of libraries needed by application. These libraries are both custom and off-the-shelf modules. The data needed by the application that can be already present in the GSSC Now platform or provided by us during the integration phase. And of course, the notebooks needed to run the applications themselves. If you are interested, you can register on the platform. You can use the data lab we integrated. They are all under the name of GMLD. And a live demo has been organized for the November 29th. So these are the applications that we integrated into Demonstrator. The first one has the scope to improve the orbit prediction by means the prediction of the ephemeris parameters. The second one consists of the prediction of the daily maps of the ionosphere. Then we try to estimate these bus messages, these bus correction parameters in the missed messages. In particular, we focused on the slow corrections and the long-term correction and fast correction, so the message types 2 to 4 and 25. And finally, we try to classify, identify, and characterize some disturbances, some source of error. In particular, we try to identify the data affected by scintillation events or multipath events. Due to the lack of time, I will focus only, or I will give you some details about only one of the applications, in particular the prediction of daily maps of the ionosphere. In this case, when looking at the temporal evolution of the tech maps, that are the total electron content maps, they can represent a time series of image frames, so the current states of the ionosphere could be inferred from the previous states of the ionosphere. So we can see the problem as a frame prediction problem. We approached the two main kind of models. In the first one, we concatenate the tech maps belonging to the same hour of the day that we want to predict. This is due to the fact that because of the Earth's rotations, the highest temporal correlation is expected among those tech maps that are 24 hours apart. Instead, the Model 2 concatenates all the tech maps from the last k hours. In this case, we found, based on our experiments, that we can allow a better exploitation of short-term spatial and temporal correlations. So our subsequent experiments were based on this kind of model. The source data we used for the application are, of course, the tech maps. They have a data rate of 2 hours. We selected data from 2001 to 2004 in order to exploit the period where the maximum of one of the solar cycle happened. But we also considered the data with the lower solar activity, in particular from 2009 and 2010. We used also additional parameters such as sunspot number and KP index. And we build the data by stacking the tech map, the values of the tech maps with repeated layer with repeated values of the additional parameters. In this way, we have data on the form of Nx and Ny that are the sides of the tech maps, K, that is the number of last K maps considered. And then we have the number of channel in the convention, in the last channel convention, that is 2 in the case of tech maps and an additional parameter repeated along all the value of the matrix. And this kind of approach enables to easy scale the input size, because when more than one parameters are considered, we have a number of channel equals to 1 plus m if m is the number of additional parameters. The output of the model has 2 channels because we try to predict the next 2 maps, tech maps in the temporal series. The model was based on a ResNet architecture with a partial and global skip connection. In particular, we have a final global skip connection among the output of the last ResNet block with the maps belonging to the related to 24 hours before in order to exploit this strong correlation. So the final result is a sort of mixed approach among the ones I explained before. And the convolutional layer are 3-dimensional for the reason I explained before. I report here only some results about the study. Of course, the GMLD enabled to perform a classical functional validation of the models by evaluating the classical metrics using in regression, prediction, classification problems, and so on. And also thanks to the integration of the ML flow, the comparison amongst the different run with the different models is made easy. In particular, the GMLD enabled to perform additional evaluation, in this sense GNSS performance evaluations, by comparing the results obtained by the machine learning models with other methods. For example, in this case, we consider some benchmark methods such as the last available map of the previous day map that are a method currently used in the literature, in classical literature. Otherwise, we implemented some other benchmark methods. For example, we implemented the evaluation of the average vertical ionospheric bias error affecting the pseudo range when the maps predicted and the ground truth maps are considered. Then the vibe is drawn into an accurate map projection, and the error map is aggregated in order to evaluate some metrics such as the mean absolute error. We found that in most of the cases a vertical ionospheric bias of 40 centimeters has been realized. In general, results about this application show the capability to forecast a different time step ahead the tech maps. So this method could be applicable in a potential GNSS service or in a receiver that for some reason is enabled to get updated information from ASBUS satellites or a third-party service. In conclusion, we can say that the demonstrator accomplished the main goal that we set at the beginning of the project, that was the study, the analysis of the possible benefits that use of machine learning could give to when applied to GNSS data. And in general, the demonstrator, thanks to this modularity, the data management capability, or the tools needed to manage the development of the machine learning models, could be applied to other use cases that could start from same data or same kind of data. Some follow-on activities have been identified, and in particular, we want to advance to approach an advanced machine learning model deployment in order to create kind of models that are suitable to run inside directly inside the GNSS receivers. So thank you. Sorry for the attention.
Thank you very much.
I finished.
We have only one very quick question. Is there any question? Okay, thank you very much, Chiara, then.
Bye.
Okay, and now let's welcome our last speaker, because this is the last talk of the session, and I hope it will be a stellar presentation for two reasons. First, because our speaker, Odysseas Dionatos, is from the University of Vienna, and usually playing at home, as this in sport is an advantage. And second, it will be stellar because he will talk about one of the most inspiring topics, the formation of stars. Please.
Thank you. So we're shifting attention now. It's big data, but it's using instruments towards the opposite direction, towards space. This is a collaborative project, the Horizon 2020 project, with the participation of the University of Vienna, University of Geneva, the Concol Observatory in Hungary. It has been also supported by a working group from the International Space Science Institute. Some of the parts I will be discussing, in collaboration with the Heidelberg Institute for Theoretical Studies. And let me give you an overview of what we're trying to do. And what we're trying to do is to better understand how stars and planets are forming. As simple as that, but it's not so simple at the end. So on the one hand, we try to compile as much data as we have available as possible, that they can provide the best description for our targets. And on the other hand, we want to use machine learning, artificial intelligence, so we try to classify, organize them so we can understand how these objects evolve. On our spare time, we also make beautiful images. So on the right-hand side, this is part of Orion. This is a color composite image of our actual data, what we use to do science. And stars are actually forming within these dense pillars of gas and dust. When we use different wavelengths, we can sort of make a tomography. So we can use images like this small inset at the bottom here. And we can penetrate through the dust and the gas in the clouds, so we can identify the different physical components and processes leading to the formation of stars. So when we're talking about panchromatic, large data collection is not only in terms of numbers of sources, but it's also in terms of lots of different wavelengths. This involves, of course, many different instruments, sensitivities, and resolutions, which creates a rather complex data set. So, to give you an overview of how we believe until very recently star formation has been functioning, a very simple sketch. In these dense pillars of gas and dust, you start collapsing because of gravitation. At the center, you have a young stellar object forming. These systems are never static, they're rotating, so you expect that flattened structures, which we call accretion disks, will soon form. Of course, as a rotating system is shrinking, you need to remove the angular momentum, the excess angular momentum, and we believe these protostellar jets actually play this role in this respect. Eventually, the material from the envelope is consumed, and we can start seeing the class 1, class 2, class 3 phases, the subsequent phases, the inner components that they lead to star formation, and the central source, the newly born star, starts appearing. The way we study these sources is at the bottom of the screen. So we use these data compilations. We get data points across many different wavelengths. We compile what we call the spectral energy distributions, and we use these different characteristics to try to classify them. So, of course, there are lots of data uncertainties. And once you do not classify properly, then you may, misclassification actually may lead to different a false estimation of timescales which are involved between these different phases. And actually, it's no surprise that just a few years before we got such observations, this is an actual disk observed in one of these very embedded sources using an instrument that is the largest astronomical instrument we have. It's based on Earth. It's called the ALMA, the Atacama Large Millimeter Observatory. It's in the interferometer. It involves 64 antennas, and it can provide the highest resolution we can get on space. So we were looking at one of these very young objects. Not only we figured out that there is a disk, but there is a disk full of gaps. And we believe that in these gaps there is ongoing planet formation. So this is only happening just within 1 million years after the formation of the central object, and not many million years as we have been assuming until now. So there is something we do not understand about the classification, or we've been doing things in a way which is not representative to what nature thinks. So what we're trying to do is, of course, our attention would go to these very embedded young sources. We would like to have as good data as possible for that. The best data to observe these objects is the far infrared. The reason for that is because they're surrounded by this very cold envelope, temperatures of around 70, 100K. Far infrared can take that. Herschel was the NISA mission observed at these wavelengths. It will most likely provide the best data until the next 10, 15 years. There is no far infrared mission foreseen for the future. So we thought we should go back and extract as good information from this data as possible. We've used many different methods, and we have used also PyTorch in terms of machine learning, trying to identify where these stellar cores. This is rather challenging for the reason that in far infrared, almost everything is emitting, including your telescope. And moreover, at 70 or 100K, you get all these diffuse background emission from the cloud. So identifying your sources in this complex variable background emission is not trivial. We believe we have done an excellent job, and we're soon going to publish a new point spread, a point source catalog for these PAX data. But of course, data collection is not only for the far infrared. We would like to have as complete data as possible. Our science test case, we chose Orion because it's the largest nearby star-forming region to us. We've been compiling data not only across wavelengths, but we went back in time. So we started collecting data from papers that they were back from 30 years ago. And this gives us, for the first time, the opportunity to make a meta-analysis or estimate how well the different classification criteria we've been using until now are valid or not. As part of this data collection, real data examples, we create these spectral energy distributions. We want to have a baseline idea of how we classify these objects. We do that using the traditional criteria. We may use what we call an infrared slope. We try to fit the slope between, say, 2 and 20 micron. Of course, you may end up having different degenerate solutions, or at the same time, we may use models to model these SEDs, assuming different physical components. Well, in terms of machine learning, another way to do that is to assume no physical components, but try to deconstruct the spectral energy distributions by just assuming some Planck functions, some Gaussian functions, and then use this information, the decomposition, to find similarities in the latent space and try to organize them in latent space. And this is an experiment that we're running right now. This isn't just a first view of these results. And it seems to be promising for the reason that what we use as typical index classifications, they seem to align with a sort of a sequence that we find in latent space. There is more work to be done and verify this data, but this is promising first results. Moving on, well, when we do these spectral energy distributions, what we're doing, we collapse the two-dimensional information, the structure of the sources, to a single measurement. So we thought, okay, well, maybe we're just losing too much information when doing that. So why not, going back, take the original observations and make cutouts around the sources. So we try to match them by rotating and flipping them in different directions so that we match them based on their morphological characteristics to the resolution we have available. And this is done actually in Vienna by the PhD student sitting here in the front, David Hernandez. And it's been functioning in an excellent way because we start seeing similarities in the structural components. We're now working in combining these images that they're, the sources which are classified based on their morphological properties, but using many filters at the same time behind that. So we get a spectromorphological classification of these objects. At the same time, when we're going to spectra, what we're trying to do is collect as much spectra as possible. We don't have many, unfortunately, just a few thousands, for example, from the Spitzer Space Telescope. And we try to use them to obtain again a classification, how we could actually learn how the sources evolve. On the left-hand side, I show results from sequencing these spectra. So we just pile them up one on top of the other. What you see here is every line is one spectrum in this plot. I'm sorry. And the grayscale tones are actually representing the flux of the spectra. And as you go in the vertical direction, these are a spectra on top of each other. So when the spectra match each other in a good fashion, then you see a rather smooth transition. Where they don't match to each other, you see these gaps. That's an excellent tool because actually we can go and trace back which sources are put together and which are not. So we can actually trace whether we've been misclassifying using the SCD models based on the spectra. Another way we're trying to do that is to use an autoencoder. So we make the requirement that at the encoding phase, we use all the spectra available we have. We try to represent them in latent space just using 2 parameters. And then based on that, to expand and populate the latent space with all the spectra that the code has learned to reproduce. And then, of course, see whether there is any clustering from these spectra, so which may signify that there is a classification based on their characteristics. So this is an ongoing progress of our projects. These are first preliminary results, and some papers are coming on the way. In case you may find it interesting, most likely there are not many astronomers in the audience today, but we're organizing a conference next spring in May in Budapest for machine learning and star formation. And with this, I would like to take your questions. Thank you.
So please raise your hand to get a microphone. Yeah, in the back of the room, I guess, at least one.
Thank you. Thank you for your talk. When you show all the different phases of the protoplanetary disk life, you show all the SED. Can you use your models also to predict the chemistry of them?
Well, to tell something about chemistry, you need spectra. So yes, indeed. In terms of spectral classification, yes. There are spectra that they have really intense lines. There are spectra that they have a very poor emission in lines. But this corresponds to the excitation conditions of the different physical components. So it might be from the disk. Quite often, protostellar jets predict much more emission, stronger emission than the disk, unfortunately. I mean, unfortunately, in the sense that if you're interested in the disk chemistry, which might lead to the chemistry you may assume that the early planets will have there.
Okay, thanks.
Thank you.
Okay, another question, maybe? Quick one. Okay, so you can keep also questions for the coffee break. Let's thank again.